Good morning. Thank you for making it to this talk quite early. Today we're going to be talking about identifying bad design objectively. And I actually want to start out this presentation with this picture of me. This was taken like 14 years ago. And I'm here pictured with my dog. Can anyone guess the name of my dog? It's a programming language. No, my dog's name is actually Java. And I found this to be a very, very fitting picture for this conference, considering we're at JFall, and here we are at a dog show, and we actually got fourth place at the dog show, and I was quite disappointed because I worked really hard with this dog. I trained him, I taught him how to sit, and I actually learned two very valuable lessons on this day. The first one being is that there's always going to be someone that's willing to criticize and judge you. I really disagreed with the judges on this one. And as a matter of fact, I think I should have probably taken the stance of the dog here, because look at the smile on his face. Just like the programming language, Java had absolutely zero concern with winning fourth place at the popularity contest. Now, the second lesson that I learned today, on that day, was that I need to take off the rose-colored glasses, because objectively speaking, the dog really only sat down when I waved a piece of beef in front of his nose, and he probably did deserve fourth place. Now, 14 years later, I stand on the JFall stage, and the tables have turned. Today, I am going to play the role of the judge, and I will be judging some other people's dogs. Okay, not really dogs. I'm going to be judging code bases, some very famous ones. So, who is the judge? Who am I? Well, I'm Ryan Susana. I'm a software creator based in the Netherlands. I like to play the piano. I'm born and raised on the beautiful island of St. Martin. That's where that picture was taken. And I'm a consultant at an amazing, I think the best cloud business in the Netherlands, and that's called Skyworks. Now, my talk is primarily focused around maintainability, because quite a few years ago, I read a very similar quote to this one, and I'm not too sure about this 80% number, but what I am sure about is that team that constantly pushes bugs to production probably costs more than my last cloud bill. Maybe not more than my last observability bill, but that's an entirely different story, right? Now, the story kind of starts like this. Someone has this magical idea for a service that doesn't exist yet, right? And for that reason, I'm going to call it the unicorn service. I know, a very unique name in the IT industry. And so development teams start working towards this service, and they actually come up with something, and it's not really a unicorn. It ends up being a workhorse that starts generating the company a lot of money, right? And after a while, developers come, developers go, and they stop taking care of their workhorse, and the horse starts to slowly devolve into this annoying donkey that is oftentimes the butt of many jokes, but you're forced to carry him along with you on your journey to find the princess, because he's the only reason people are paying for your services or your silly DreamWorks movie in the first place. Now, unfortunately for the other donkeys, the code bases, they don't really have a happily ever after story. There's no dragon to come and save them. Usually these code bases, they start to die out quite slowly. As a matter of fact, a previous customer of mine, they had a service. It wasn't called the unicorn service. It was called the narwhal service. I know, right? And they've been trying to phase it out for like the last 2 years. And they're actually replacing it with something called the unicorn service. Go figure. And this is a service written in Java 11, so it's not even very old or anything like that. Now, this really annoys me because I see it over and over and over and over again as a consultant. So what we're going to do is we're going to take like a 5-second moment of silence just to think of all the code bases that we just let die out because of our neglect. Yeah, you should be ashamed of yourselves. But my question really was, why does this happen? And I really blame this on the second law of thermodynamics. which states that if you leave a system by itself, the entropy of that system can only increase, right? And a great example of this is I was working on a JavaScript project a couple of years ago, and I left that project just alone for like 9 months. And after 9 months, the project like failed to build. There were like 5 missing packages and about 10 developers asking for donations, right? And this is a perfect example of entropy happening. You know, the world around my software system just changing, and my system had to adapt, and it just didn't. And it turns out that maintainability is something that is not urgent, right? No one wakes up out of bed and say, oh, we need to hit that refactoring deadline. No one does that. But everyone in this room probably has a feeling that it is important. And what is this maintainability exactly? So the best definition I got on this was the ISO 25010 standard. I know it's a lot of words. You can take a picture of it if you want to. I'm not going to reread the sentence. I like to simplify it a bit. And maintainability, to me at least, is the ability for a software system to have change and to adapt to changes around itself, right? And we measure maintainability by observing a system and its components. Now, what are components again? And a few years ago, I've been asking some architects to say, what is a component? And they usually told me something along the lines of, it's the building blocks of your system. Very vague language. So it turns out components are like a very loaded term in engineering and mathematics. And when you say the building blocks of your system, it's way too abstract. I wanted it to be more specific towards software engineering. So there is this wonderful guy called Mark Richards. And he has another definition for component, and it uses more lingo in our world, right? It's the physical manifestation of a module. And I love this definition because it uses terms that are concrete and that I understand. You know, physical manifestation, that's obvious. It exists somewhere. You can feel it, you can touch it, right? A module comes from modular programming, and technically it's a routine and it's related instructions, but we live in 2023, it's just a group of related code, right? So the physical manifestation of a group of related code. Now, turns out that components can be observed from many abstraction levels. So a good resource on this is the C4 model by Simon Brown. And a lot of the times architects, they start recognizing components from the directory level upwards. So in a Java world, that might look something like a package. Zooming up one abstraction level, it might look like something like a Maven module or a jar filled with packages. Zooming out more, it might be a project that's filled with modules, or a service or something like this, a container. Zooming out a bit more, it might be a set of services behind a unified API gateway, or a third-party service like Google Search or Google Maps. Now, today, just for the sake of coherence and simplicity, we are going to start viewing the system as application architects or as software developers, and the abstraction level of the day is packages. Now, it turns out that not all components on the same abstraction level are equal, right? And there are different ways to measure them. And we're actually going to start off with measuring something very simple. You probably are familiar with it. It's called code complexity. And complexity really boils down to, if you're talking about complexity in general, it really boils down to the intricateness of a software system, right? But if you're talking about code complexity, what you're really talking about is the denseness of logic, right? So one way to measure code complexity in a component, just look at the lines of source code, right? Very simple. Another way is something very famous. It's called the Halstead volume. So you're just counting the number of operators in your code. Third way, probably the most famous of them all, is called cyclomatic complexity. So you're counting decisions in code blocks. I'm not gonna, you can do some research, it's quite popular. But my favorite method of them all is called white space-based metrics, or indentation-based metrics, or nesting, if you will. And I like nesting because it's very natural to the way I read code. So I would say that the code on exhibit B is a lot more or a lot less complex than the code on exhibit A, even though they do exactly the same thing. And the Halstead volume on A is higher, the cyclomatic complexity on A is also higher, but more importantly for me, the indentation is a lot higher. And it turns out that indentation strongly correlates with all complexity metrics that we find for software. So it's actually a very good proxy metric. And you can, it's very easy to calculate because it's universal across coding languages, not just programming languages. And like if you ever debug some huge Kubernetes manifest, you probably find the same, right? The more indentation you have, the more complex your deployment becomes. Now, it turns out that complexity is, in all its forms, not just code complexity, is oftentimes lead to undesired outcomes, right? So typically speaking, the agility of your company, it decreases a lot. But it can also lead to effects such as a decrease in performance, security. You might just start creating more bugs. Complexity is, you never wake up and say, hey, I want things to be more complex, right? It's not a good thing. But is complex code bad code? What do you guys think? Everyone says yes? No? Some say no? Well, it depends. And this is a common trend in most of the software architecture answers. Was the complexity on accident, or was the problem just a complex one? That's what you're really answering. And really, it's very hard to decide as a developer or an architect just by looking at some metrics, just some numbers, if this was too complexly implemented. However, you can still measure complexity in general. And we're actually going to do a demo of complexity. But first, I want to unveil a project that I've been working on together with my co-contributor for the last year. And it's called ArcStats. And it's a way for me to generate and visualize insights on large code bases. Right now, we support some languages. So we support Java, Kotlin, Scala. We also support C# and PHP. And we're just aiming for more and more. And it's an open source project, because there are some similar tools that are not. And we're very excited to show you it. So I'm actually going to hop into a demo right now of ArcStats. So it's really just a CLI application at the core. So everyone can see this, right? Yeah? Great. So what I have here is I have a little bash script, and I just cloned a random clean architecture repository that I found somewhere. I haven't really dived into the code much. And you can generate metrics for your architecture by just running this arcstats export SQLite command. And what that does is it generates a set of tables for you in SQLite that, which is basically the output of your analysis. So here are some queries, for instance. I get a summary of the code base. I get to see all the tables that ArcStats generates. And I get to see the components or the packages that ArcStats has found. So I can go ahead and run this. And actually, what I'll do is I'll run this in less so you can see it. So here you just see some of the metrics that ArcStats generates, but also some of the tables. There's a lot. In total, ArcStats generates 42 different metrics on your code base. And here are just the packages. But I'll do you one better, because I mentioned that it was an open source CLI, but it's also a web, it has a complementary web app, right? And I'll go ahead and demo it to you. So you can access this web app, and nothing goes over the network, so you can just use it for your own development, right? And you just import that same DB file. So I've made some analyses of just some popular Java repositories. So the first one I'll take to demo complexity is Mockito. And I can go into the component comparison view, and I can basically compare components amongst themselves based on some of the stats that ArcStats generates. So here you can see all of the stats that ArcStats has for this analysis. And I'm going to actually select the indentation max stat, which gets the max amount of indentation in a file in a component. And I can see one stands out here. It's called creation byte buddy. All right, so let's zoom in on that a bit. And here I can see it has a max indentation, that's tabs or 4 spaces, 2 if you're a psychopath, of 22. That's a lot. So if I go here to the file view, I'm actually going to take this off, and I'm going to, so this one, I can see that the max amount is in this file, the inline bytecode generator. So I've actually opened this inline bytecode generator in GitHub, and you're gonna. This is what complexity really looks like, right? So we start here. Okay, it's has a lot of dependencies here, and then here. Look at this, right? Now I'm quite an experienced Java developer. I'd like to think, and when I look at this, I get scared. Because imagine trying to understand this, right? And then there's an entire novel written here just to understand this method that changes some sort of internal state. This is what code complexity looks like. And it's my gut feeling that this class in general is just simply way too complex. It can be simplified. But, I can't really say that objectively until I make a pull request and actually verify my hypothesis here. But it's a hypothesis. It can be true. So we're gonna move on to the presentation here. And we're gonna talk about good old coupling. So who has heard low coupling, high cohesion before? I just raise your hands. A lot of folks. Nice. Now, I have a metaphor here that I'm gonna use. This is just a household. And it's me and my partner here. And we have 2 kids. And our kids, they depend on us somehow. And me and my partner, we also depend on each other, right? Now, this was not coupling. Those were dependencies, right? Coupling goes a bit deeper. Now, when you're talking about coupling, you're really talking about the knowledge that one component has of another, right? And for instance, I'm a stay-at-home dad. So I depend on my wife here to pay the bills. Right? And another way I like to reformulate it is the reasons that I depend on other components. And technically speaking, there's this nice book of Uncle Bob, Robert Martin. I think it's his best book. It's called Agile Software Development. It's written in 2002, where he describes this in great detail. And the real technical term that he has for coupling is called the number. We'll get to that soon. But let's say I depend on her to pay the bills. I have a teenage daughter. She needs food, and she goes to Muay Thai lessons. I have a smaller son, so he needs a bit more attention, and he needs to borrow my computer for Minecraft. And of course, he also needs food. Now, from my perspective, the reasons why other components, or people in this case, depend on me is called my afferent coupling. And the reasons I depend on other components, or in this case, people again, is called my efferent coupling. Now, this is what Robert talks in one of his chapters in that book. And it turns out that he calls efferent coupling a reason for a component, or in this case, a package, to change, right? And looking back at this example, if my wife stops paying the bills, I have a reason to change. I got to get my act together, right? I need to start working probably. There will be probably less food. I will probably affect my children somehow. Probably have less time to spend with them. Now, and if you take the efferent coupling, so that's that one at the top, and you divide that by the total amount of coupling, you come up with this stability metric. And this stability metric measures the reasons a package has to change. Now, it turns out that unstable code is irresponsible and dependent. So code with a high instability score is irresponsible and dependent, but stable code is responsible and independent. Now, who thinks that stable code is good? Raise their hand. Right? To the naked eye, it may seem so. But it turns out that stable code is code that is simply hard to change because there's no reason for the code to change. And what we notice in the first part of this talk is that sometimes code has to change to adapt to its surroundings, right? So there's another metric that he describes in this book. It's called abstractness. Now, abstractness is the counter to stability. And he says that this is how you calculate abstractness, by the way. You take the abstract types and you divide it by the total types. All right? And he says that a component should be as abstract as it is stable so that making change to that component, it doesn't get in the way of itself, right? And that's what this abstract metric is all about. Abstractness metric is all about. Now, the ideal balance, and it comes from his love for astronomy, is called the main sequence. And I kind of got a deep dive about this because one of my colleagues has a PhD in astrophysics, and he kind of explained me what it is. It all went over my head. It's kind of real engineering, and we do fake engineering. But the ideal balance is called the main sequence, and it kind of looks like this. So let's say that on the y-axis here, I plot, or the vertical axis here, I plot abstractness, right? And on the horizontal axis, I plot instability, which are both numbers between 0 and 1. This line in the center here is called the main sequence. And ideally, you want your components to sit on that line so that you have that balance of abstractness and instability. And what you're seeing here is called the distance to that main sequence. And if you're too far away from that main sequence, experts say that you start to experience some bad things with your code. So they call this right here the zone of pain. Now this represents code that is just hard to change, right? And this code, the code that is too abstract and too unstable, he simply calls it useless code. It does really nothing. Now, to calculate the distance to main sequence, you take the abstractness, you add it to instability, and you subtract 1, you get the absolute value there, and that's the distance to main sequence metric. Now, let's actually jump in and demo this distance to main sequence. So I'll hop here in my thingy here, and I'm actually going to navigate to this component plotter view. Now, I have the project Elasticsearch open right now, and here you can see where all of the packages within Elasticsearch, they fall with respects to the main sequence. And so about this component plotter view, you can actually from 3 different dimensions track all of the statistics that ArcStats generates. So the bigger the circle here, the more lines of code is that package. So you can see quite a few packages for Elasticsearch are very far into the zone of pain, including this big one right here called cluster metadata. It sounds unstable, metadata. Oh. Now, that's one way to view the distance to main sequence in ArcStats. Another thing that you can look at if you want to visualize coupling, on the other hand, is you can go to this main sequence or matrix view. And this basically plots all the components that has been recognized in Elasticsearch. And you can see them on the y-axis here, but also the x-axis. And this graph visualizes how coupled 2 components are to each other. So if I order this by, let's say, the afferent coupling, and I reverse the list, now you can see components in the top left that are very coupled together. So the darker the box here, the more coupling exists between 2 different components. And you can see here, this one has a lot of coupling here. About 59 files in index query also refer to X content, whatever that may be. And you can kind of see that and debug it this way. But another way that I like to do it is by going to the component walker, which I'm going to talk about in just a second. So let's get back to the slides. Now, I want to talk about component cycles. And I hate these things. And because if it's one thing you take away from this talk, is that component cycles are objectively bad. Now, here is an example of 2 component cycles. Package A depends on B, but B also depends on A. That's the first one. The second one is A, B, and C all depend on each other in kind of a circle, right? Now, like I said before, cycles are objectively bad. Very bad. Like, stop it, guys. I see them happening a lot in class-based, object-oriented programming languages. It feels like Java and C# developers alike are simply attracted to putting cycles into their code for some reason. I don't know why. And the reason why cycles are bad is that, first of all, they increase complexity, right? Through adding unnecessary coupling. And they just make code harder to understand. And that can lead to some very undesired outcomes, right? And they also make code harder to test because it's harder to isolate code because if 2 models both depend on each other, one cannot exist without each other. So it's harder to test them in isolation. Now, there are a few metrics that I have for cycles. In ArcStats, we implemented this algorithm to find the number of short cycles in the code base, which is very handy if you want to find cycles in your code base that you can easily get rid of. There's another one, you can just track the number of short cycles per component, and this way you can find the problematic components from a cyclicity standpoint in your code base. This comes from graph theory. It's called strongly connected components or strongly connected subgraphs. And it basically it splits your component graph into different parts and tells you, you can find what the largest cycle in your code base actually is. And a less, I guess, important metric is called just the pure number of cycles. And this is very computationally expensive to calculate. We ran it on the code base you'll see just now, and I ran it overnight. We've generated billions of cycles from that code base, and it still didn't finish, and the program actually crashed. So you probably don't want to see all your cycles. It's overwhelming information. Now, we're going to do a quick demo of cycles here. And the code base, and it's just because I love to pick on Elasticsearch, it's going to be Elasticsearch. Now, I can navigate, so I'm going to navigate from the home just so you know how to get there, to the component walker. And one of my favorite ways to, so actually let me explain what the component walker is. So what happens is on the left side of the screen, you're seeing your afferent coupling, or yeah, your left. And on the right side of the screen, you're seeing your efferent coupling. The middle is the current component that you're on. And at the bottom here, you're looking at the current path that you're following. And this component walker allows you to navigate your component graph like you're kind of walking through it, and it can help you debug the cycles in your code base. So one thing that I like to do is I like to just take, like, let's take this one, just a random package in the code base, and then I just like to start clicking, and then, whoop, we found our first cycle. It's one way to do it. And here we see a cycle, and it's visualized in your path here between stream and bytes. And every time this number grows, the cycles increases for that specific component. And I can actually zoom in here and navigate the cycles to see where they happen. And I can go both ways. And I can go back and forward in the path here. But another thing we have is we have this dialog. And it's called, let me reset the path. It's called just select cycles. And this is just all the short cycles that ArcStats has found within Elasticsearch. And this page is 12 items long, times 400 is a whole heap of cycles, 4,800 cycles. That's a lot. And an interesting one that I found, right, and I kind of wanted to show it, is one between REST and HTTP. Now, if you know a little bit about the web, you know that HTTP is a layer 7 protocol and REST is just a standard that sits on top of it, right? So it makes sense that if I navigate to the REST package, that it somehow depends on HTTP, right? Yeah? Everyone agree? Now tell me why HTTP depends back on REST. I don't know. This conceptually just doesn't make sense to me. And I've actually dived a bit into this example. So if I zoom in here on the dependency between HTTP and REST, I can see that in the HTTP package, there's a bunch of classes that depend on REST, but there's this specific one here called default REST channel. That sounds like it's just a misplaced class. And it's actually, I looked into it a bit more, it's the most complex file in this package. And I have it open here. So let's check it out. So and this is what I mean with Java and C# developers overcomplicating things. We have a default REST channel that extends abstract REST channel, but it also implements, you guessed it, REST channel. And in this entire 1 million line code base that I scanned for Elasticsearch, there are exactly 2 implementations of REST channel. But the implementation is split between 2 abstract classes, two implementation classes, an interface, and also everything extends object, right? So there's like 4 levels of inheritance just to define this concept of a REST channel. This is overly complex. It's probably unnecessary. It's just a hypothesis again. Yeah, we can scroll down a bit. I think something has been poorly designed here. It's probably something that we can even refactor away. So this is how you can look at cycles and kind of refactor them away. But let's look at some of the cycle metrics, right? So if I go to the component comparison again, I can go to cycles, and I can just look at the components with the largest amount of cycles, and one immediately bubbles up. It's called this Elasticsearch action package, whatever that may mean. Now, of course, I dived into this example a bit. This action package is part of how many cycles? It's part of 4,000 different cycles. Crap. And we can visualize that. And I like to call this diagram the spaghetti and meatballs diagram. If I just click this to see all the cycles that it's included in, it looks like what? A big ball of mud. Or spaghetti, if you like that better. Doesn't have to be. It can also be in a monolith. Now, it's not a distributed ball of mud. It's just a big ball of mud. And here you can also see and visualize what's happening with the cycles, and you can see how they grow. And what's happening with this action package is that action package actually does 2 things. It's a registry for all the actions that exist in Elasticsearch. That's one. But it also provides the common interface. So you can imagine a lot of actions within Elasticsearch depending on that common interface, but the registry also needs to know of that action. So that's actually a pretty easy problem to solve by just splitting the registry part from the common interface part. So this is just one example here. So let's actually go back to the slides. I had enough of these cycles, yuck. Now, I'm going to talk a bit about graph and network theory, and this is, so what you just saw was more traditional software architecture metrics. Graph and network theory is a lot less explored, and I want to specifically dive into this concept of graph centrality. Now, what graph centrality is if you look at a graph, especially a directed graph, the graph centrality tells you where the important vertices are in that graph. And in a software component graph, that roughly translates to the important and influential structural packages or components in that component graph. So I love this metric because it helps me I love these metrics because they help me identify where the important structural components of the code base are. So one of my favorite graph centrality metrics is called betweenness. And it essentially measures how in between a component is with respects to all the other components. If you look at a path between 2 components. So the bluer the component in this graph, the higher the betweenness score. This blue node or blue component is apparently more in between than them all. And there are many more centrality metrics, but these are my favorites. Now, the first one is the betweenness metric that I showed you just now. Another one is the Google PageRank algorithm by Larry Page and Sergey Brin. It's just link analysis, and it looks for the important web pages, or in this case, components. Another one is called residual closeness. Now this one I really like. It's actually a quite new graph metric. It's only invented about 10 years ago. And it basically measures that if I were to remove a component from the graph, how does it affect the structure of the entirety of the code base, or the closeness or centrality of the other components in that graph. So we're actually going to demo some of these metrics and how they might be useful for identifying bad design. So let me open my thing here. So what I'll do is, oopsie, component plotter. I have the Neo4j code base open, and I chose Neo4j because I'm looking at graphs, right? And what I can do is I'm going to change the radius here, By the way, the plotter has some really nice presets here that you can use that I find handy. And I'm going to change the radius of the circles to just betweenness. And you can see where the important structural components are with respect to the distance to main sequence. Another way that I like to find the important structural components is just by looking at comparison and scrolling down to like the betweenness metric. And one immediately pops out. And what I like about betweenness is that oftentimes I can find the core domain of an application by looking at it. So the kernel database for Neo4j makes a lot of sense. And another one I'll look at is called PageRank. And what I usually tend to find from the PageRank algorithm is actually the supporting subdomain. So I find the exceptions package, right? The API exceptions, the common, the util probably. Oh, I find GraphDB here as well. The utils, helpers, these types of components I can find from the PageRank algorithm. So this is how I like to use different graph theory metrics to find important structural components within code bases. Now, we're actually going to go back to the slides here. And the last thing that I want to kind of cover for this talk is this whole idea of developer activity. And it turns out that if you run git log in a Git repository, you can find out who made the change. You can find out when they made the change, what files or components have been changed. You can find out how much of those files and components have changed, and the reason for the change in something like a Git message, right? Now, it turns out that we don't touch all the code all the time. And I actually read this in a fascinating book by Adam Thornhill called Your Code as a Crime Scene. Very great book. Give it a read. And by observing the amount of component changes, you can find where to invest your refactoring efforts. So what you find by looking at component changes a lot of the times is the code that changes frequently. So if that code is poorly designed and it's wasting everyone's time, that's probably the best place to put your refactoring efforts into. Another thing that looking at component changes will tell you is how often two or more components change together. So it's another way of viewing coupling, actually. So let's demo a bit of these Git metrics in ArcStats. So ArcStats generates a lot of Git metrics. And one thing that I like to do, and here I have, Hibernate. This is one project. If it's one project, I like all the projects on this that I'm demoing here. So one project I like to avoid is the Hibernate one. Because anytime I feel like I need an ORM, I think things are getting way complex, because they're probably more complex than just regular SQL queries. But if I take this preset here, I take the distance to main sequence, and I look at the components that change the most, I find very big ones here. So this Hibernate persister entity package and this internal package and this dialect package, they fall in the very bottom left of that distance to main sequence graph. And what I'm going to assume, my hypothesis here, is probably that the maintainers and contributors of Hibernate are not having the greatest time right now. Because according to that theory from Uncle Bob, it's painful. It's also painful to look at, really. Oof. Now, I'm going to go back to the component matrix view. And here, it gives you so I'm going to order these components now by, let's do it by something like betweenness, but in reverse. Now, if I change the way I scale the colors, I can actually see how logically coupled two components are together. So I'm going to just look at the amount of shared commits that they have. And I can go here, and I can see that this internal package and this service provider interface, 39% of the time you're changing the engine, you're also changing internal. So that's kind of saying that maybe two concepts within this package kind of belong together. And you can actually see the commits that happens here. And I find this to be very valuable information because it kind of proves that those coupling metrics, right? So if I go back to coupling here, they're not even afferent and efferently coupling that much in relationship there. Now that's interesting. That's something that I would actually look into. So this is also how you can use these Git metrics to kind of find out more about not the technical aspects of the code, but the human behavior surrounding the code, the developer activity. So you kind of get to view your code base from two different perspectives. There's a lot more you can get out of Git metrics, but we don't have time for that, unfortunately. And I'm actually going to conclude this talk, right? And we touched on just defining maintainability in general. We looked at how we can decompose systems from just the C4 type of model. We look at complexity, the traditional software architecture metrics. We take in a step into the graph theory route, somewhere that's a bit less explored. And we also looked at some developer activity metrics. Now, there are 42 different metrics, like I told you. There's a lot more to talk about. I can talk about this topic for till kingdom come, but I won't, unfortunately. And I actually, I want to talk a bit about what's kind of next for this ArcStats project. Well, we are in the process of doing support for more languages. Like I said, we support Java, Kotlin, PHP, Scala, and C#. But we're aiming for many more. I think the next targets are going to be C++, Golang, and ECMAScript. And we want support for even more metrics. We have some quite novel ideas here and doing more research into the topic. I encourage you all to go to the GitHub repository by scanning that QR code, giving it a star if you appreciate the work that we've been doing, and actually trying out the project yourself within your own code base. And another thing that I want to touch on is this whole idea of integrating ArcStats into with generative or AI or LLM. I know we have to do it, right? There's some very, very interesting things that we're looking into, and maybe we can have a discussion about it after this talk. And on that note, I thank you all for listening to me ramble about software architecture metrics for the last 45 minutes or so. And yeah, thank you for having me. Thank you for listening. And do we have time for questions? Yeah? Any questions?
So you scan Elasticsearch, that's quite a big code base, I figure.
Yes.
How long does your tool take to analyze it?
So it depends. So ArcStats is structured as a micro-kernel architecture or plugin-based architecture. Depending on the extensions that you use, the scanning will take longer. So running git log on Elasticsearch for the entire history of Elasticsearch takes 2 minutes, just running that git log command. But running just ArcStats with the Java extension takes about less than 10 seconds.
And it's fast.
Yes, it's pretty fast. Yeah, it's written in, it's also compiled to Go. Compile time is also fast if you want to compile and build it yourself. So it's quite a swift product. Any more questions? Yeah. So where do we go on after, how do we go on after we've identified bad design? So this talk that I have is actually, it's kind of a part of a workshop series that I have that I give to customers. And the first part of the workshop is called Preventing Bad Design, which I dive into how to prevent these things from happening. And there's a great book on this topic. It's called Building Evolutionary Architectures by Neil Ford. The second part of my workshop is actually this part. Okay, we probably have bad design. How do we objectively look at it? So that's what you saw here. And then the last part of the workshop is actually something I like to call addressing bad design. Now, there are no silver bullets for any design issues, and there's a lot of the times different ways to roam, right? But there are different practices and tactics that you can use from an individual contributor level to a team level to an entire organization level to address bad design that exists already. So one practice that I like to do is if I'm an individual contributor on a project, I like to just leave code bases better off than how I find them. That's just a practice that I like to do, and I do that objectively by looking at some of these metrics. On a team level, what I like to do is I've been working on a team at bol.com, and what we do is we create work for features, of course. I worked on the search team there. But we also created work for just improving things. So I remember us spending like iterations on improving how we generate some search aggregations. And that really, it needs to be kind of in the team culture. And you can do that just by assigning Jira issues and tickets. Another thing from an individual, from an organizational perspective, is to first of all be aware of these problems. So typically speaking, you kind of need a champion within the organization that kind of stands up and say, hey, we have a problem because all of our developers are kind of burned out right now. We need to look at the way we maintain our software. And then you can use a tool like ArcStats to kind of see the health of your company's code bases over time. So, and you track that, and sometimes what you can do is you can have targets there, but I kind of like to stay away from targets, but you kind of track that over time and try to improve it holistically. And I have a couple workshops on that where I can give some tactics there. So you can prevent it, but you can also address it. But you also need to identify it, right? Yes. And any more questions?
Can you integrate these architects in your, let's say, making build?
I mean, I did say that it is just a CLI tool. So you can do things like run queries for like, make sure the number of cycles don't increase. Or you can write different, they call them fitness functions. And fitness functions are basically a way to validate the correctness of your software architecture. And you can build it right into something like your CI/CD system. So make sure you're not introducing more cycles. Make sure the code health doesn't go down. These type of, just like how SonarQube does. Yes. Last question, or how much time? Yes.
How well does the tool work with multiple repositories? For example, we have an application with multiple modules and stuff like that. Does the tool also handle that?
Yeah, so we've been thinking about this a lot. And within for the generated SQLite database, it generates a report ID that you can then link to something like a Jira issue or a task, but you can also link it to a repository, for instance, and just generate a massive SQLite database to kind of have a very big analysis, drop that into something like Power BI, and you can see holistically what the metrics for your organization look like. So we're still really working on that part. I like that you asked that. But there are still ways to do it right now today.
Are the visualizations on the ArcStats website a premium feature?
They're completely free. So because browsers have become very powerful over time, nothing actually goes over the network. So you can drop a gigabyte large ArcStats database file into the web browser, and it will query via WebAssembly and some JavaScript magic. It will query the ArcStats data in browser for you. So and I just host it as a static website. I don't pay anything for it, so why should you? That's it? Thank you.